Hi, this is Kip Neiman again. So this is the fifth part. Let me double check that. 1, 2, 3. Yep, the fifth part of my Fluent Example series. And so now I want to talk about the contents of the UDF called wallprofile.c. So what I've done here in this slides is I've gone through each line and explained what each line indicates. So the first line is this include UDF.h. This basically imports a header file. So a header file is a common term in the C coding language. And a header file contains makes a bunch of commands available to you when you start programming. In this case, the header file contains all the Fluent functions, commands, and macros. Basically, they're all the things you need to interact with the Fluent simulation. The UDFs use the C coding language with many custom features introduced from the UDF.h header file. Mainly, you will use these custom functions, commands, and macros when you're making UDFs. Maybe you will define variables in between, but these custom things make up the bulk of your code, typically. The next line 3, says define PowerVal2. Basically, what this does is this defines a global variable called PowerVal and assigns it a value of 2. The advantage of global variables is they can be accessed inside of any of the functions in this .c file. In this situation, PowerVal could also be defined as a local variable in the UDF. So in this case, it would be like lines 7, 8, and 9, which are local variables. I defined it as a global variable here just to show how to do a global variable essentially. Next is the first line of the UDF. So the UDF starts at this defined profile, and there's this open curly bracer, and it ends down with the closed curly bracer down here. This UDF is a defined profile UDF. Basically, the defined profile is for defining like a temperature profile or a pressure profile along a boundary condition, for example. In this case, I'm going to name it wall profile underscore temp. So this is whatever you name your UDF goes here. The second argument, in this case, is T1, and the third argument is I. These are basically variables that are passed between Fluent and the UDF. So T1 is a pointer to a thread, which is basically a zone in Fluent where the boundary condition is applied, and I is the index that identifies the variable that is to be defined. I is set when you hook the UDF with a variable in a boundary condition dialog box through the graphical user interface. This index is then passed to your UDF by ANSYS Fluent Solver so that your function knows which variable to operate on. Next line, which is line 7, this declares a local variable, specifically an array representing position. In this case, X contains 3 entries representing the X, Y, and Z coordinates. And you can access each one of these by typing in X0, X1, or X2. The reason why it starts with index 0 is because this is C programming language. If you've ever used MATLAB will instead start with an index of 1. It's just the way that the indexing works in this code. And so you can see where I accessed actually the Z direction on line 14, for example. This nd underscore nd is used instead of a number because it sets the length of X to be whatever the current simulation is using. So for a 3-dimensional simulation, position has 3 coordinates, so X will be given a length of 3. And for a 2-dimensional simulation, there's only 2 coordinates, so it'll be given a length of 2. Real Z direction, the next line, is just I'm declaring a local variable called Z direction, which I will fill in with values later. This line here, which is line 9, real time equals current underscore time. Basically what this line is doing is pulling the current simulation time from Fluent and storing it as a local variable called time. This all caps current underscore time is basically a Fluent macro that pulls the current simulation time. And so you can actually give this any name you like. I called it time, but it doesn't have to be time. And basically, to be clear, this command gets the time in your simulation, the simulated time, not the real world time that has elapsed while your simulation is running. So this is commonly a confusion for me in codes is When it says simulation time, does it mean the time in the simulation or the time in real world? In this case, it's the time in the simulation for this particular command. Next, I declare a variable called f1 to represent a face. And the reason why we do this is because we're going to iterate through all the faces later, so we need to define a variable. Then there's this begin f loop. So this is a custom Fluent thing. So basically, it starts with begin f loop, and then you enter in f1, the variable representing faces, and then t1, the variable representing the thread, and then is an open curly bracer, and at the end you have a closed curly bracer with an end f loop. Basically what this does is this loops through all faces in thread T1. Everything inside is repeated for all faces that are part of the thread T1. The first command inside of this loop is f_centroid. This is basically a Fluent macro that finds the centroid coordinates of a face. So the centroid coordinates are this first, so it fills in x. It gives x the centroid coordinates of a face as it iterates through the faces and sets x equal to those coordinates. F1 is the face and T1 is the thread. So the result of this is that x will now contain our centroid coordinates for one of the faces in the thread. Next, we have the z direction equals x2. Basically, I'm just pulling the z coordinate from x, which was, so x got those coordinates from the previous f centroid command. Then there's this f profile. This is another user-defined UDF custom macro. Basically, this sets the boundary condition to a temperature in this case. So a macro that stores a boundary condition in memory by referencing index I for a given face f1 and thread t1, and is nested within the face loop. This is the begin f loop. Here I set temperature to be the function of the z coordinate with respect to time. And how do I know it's temperature? It's because, and I'll show later, it's when you actually hook it to when you hook it as a UDF in Fluent, you're going to hook it by specifically entering it in the temperature setting. So I'll show you how to do that later. The specific equation I picked for f profile is basically 300 Kelvin plus 100 times the z direction to the power value. So in this case, power value is 2, so I'm doing the z direction squared. This pow is a C command for doing powers. And then I did plus 50 times time. And you might ask why I did this equation, and there's really no reason. It's kind of a meaningless equation, but I wanted to show how you can use the z direction and time in the same equation. So next, I want to show how do you actually hook your UDF to Fluent. So first, what you need to do is you need to take your UDF. So I'm going to copy this. This is my UDF stored elsewhere. I want to go into my example. In this case, I'm working on this example simulation. I want to go into the files, not the backup, because the backup is a temporary that runs while the simulation is open. So I go into the files, go to DP0, go to FFF, go to Fluent, and this is the location I want to paste my UDF in. Then what I want to do is go to Fluent, and along the top here, where it says domain physics, I'm going to go to user defined and click on functions. And then, so there's basically two options. You can interpret the functions or compile the functions. Basically, interpreting the functions is very limited in scope. It's simpler to use, but it also has many limitations. So generally, I will compile things. And so to do the compiling process, you click on compile, and this box comes up. What you usually click add, and it'll actually take you right to that folder where I added the wall profile UDF. So you click on the wall profile and click OK, and then you click build. And it'll say make sure stuff. Okay. So what you'll see Fluent does some thinking, and you want to look at this result, and you want to look for any sort of errors. So if there's errors, that usually means that you messed up in your code and you need to go and fix your code. But in this case, there's no error. So I'm done. I clicked build. Now I can click load. And so now my UDF is loaded in the simulation, but it's not what we call hooked. And so to hook it to the simulation, what I want to do is I want to apply that profile. In my case, I'm choosing to define it along the outer wall. So that's the outer surface of our tube. So I'll go to boundary conditions, wall, and I'll double click on wall. And I want to go to thermal because I'm dealing with temperature. And this is where I was talking about how does it know that I'm picking temperature as my variable I'm manipulating, because I'm going to click on temperature here. And where it says temperature, instead of 300 Kelvin, I'm going to hit the down arrow and go to UDF wall profile underscore temp and click OK. So essentially what this means is my UDF is now hooked into my simulation. What I will do is I will save the workbench file and I will run the resulting simulation. So I'm going to go to initialization. I'm going to reinitialize it, run calculation, calculate. So this is the same process as before, where at each iteration, it starts with a higher residual, and the residual represents how much the iteration's results are changing upon every iteration. And so as the simulation converges to a value, the residual should decrease. And so for each iteration, it decreases until it reaches the specified tolerance. And so now I have simulation results. What I can do is I can close Fluent. And I can open CFD Post. I'll show how that looks now that there's actually results there. So I'll double click on results and wait for it to open. So I already had my plane created. If I go to plane 1 and color, temperature, and hit apply, it should update my results. So now if I hit play, you can see it was really short because it played about, I'll put, if you hit this little infinite button here, it'll repeat it over and over again. You can basically see over this short period of 10 time steps, which is 10 seconds, it starts out cooler and it heats up. And so this is one way in which you can look at simulation results. Okay, so I will see you on the next section.